Welcome to Optical Fiber Communication Laboratory menu. In today's session, we will discuss Practical 8. Request to like, subscribe, press bell icon, share and comment. This is sample of certificate. Index. In earlier video, we have discussed example related to optical fiber waveguide, transmission characteristic of optical fibers and cables, optical fiber connection, joint, coupler and isolators, optical source, the laser, optical source, LED and optical detector. In today's session, we will discuss Scilab code for a given example of digital transmission system. Practical 8. Digital transmission system. Aim to write a Scilab code for a given example of digital transmission system. Software is Scilab 6.1.0. Theory: point-to-point links. The simple point-to-point link is as shown in figure 8.1. It consists of the transmitter on one end and the receiver at the other end. Information source, optical transmitter which consists of LED or laser, and optical fiber with multimode fiber or single mode fiber, optical receiver which consists of pin or avalanche photodiode, and user. Optical transmitter consists of emission wavelength, spectral line width, output power, effective radiating area, emission pattern. Optical fiber consists of core size, core index profile, BWO dispersion, attenuation, numerical aperture, MFD. And optical receiver consists of responsivity, operating wavelength, speed, and sensitivity. System requirement for the point-to-point link. The desired transmission distance required for the data to transform from the source to the destination. The second, the bandwidth of the channel or data rate. And third, the bit error rate. Link power budget or optical power budget. Need of optical power budget. We need to calculate the link power budget, which makes sure that optical fiber connection have a sufficient power for an appropriate operation. Optical power budget calculates the maximum amount of power. Optical power budget is nothing but the difference in dB between the transmitted optical power in dBm and the receiver sensitivity in dBm. Optical power loss model. Figure 8.2 shows the optical power loss model for a point-to-point link. With transmitter consists of connector, optical source and fiber fly lead. This is splices, optical fibers, this is the connectors, and receiver consists of connector, fiber fly lead and photodetector. The optical power receiver at the photodetector depends on the first, quantity of the light coupled into the fiber, second, losses occurring in the fiber at the splices and connector, and third, the loss generated by each element in the link as expressed in dB. The loss in dB is given by loss equal to tan log 10 P out by P in equation 8.1, where P out is equal to optical power leaving the loss element and P in is optical power entering the loss element. The total power loss P suffix T in a point-to-point link is given by P suffix T is equal to P suffix R S minus P suffix R, equation 8.2, where P suffix S equal to source power and PR is a receiver power. This equation 8.2 can be written as Pt is equal to 2Lc plus alpha L plus system margin, where Pt is a total optical loss, Lc is equal to connector loss occur at the source and detector, L is a transmission distance, alpha L is a losses in the optical fiber. Equation 8.3. Rise time budget. The rise time budget determines the dispersion limitation of the optical link. Once the link power budget has been established, the designer can perform the system rise time analysis to make sure that the desired overall system performance has been met. Total rise time. The total rise time is a root sum square of the rise time from each contributor to the pulse rise time degradation. It is denoted by T suffix system. The T suffix system is equal to sigma I is equal to 1 to n Ti square 1 by 2, where Ti is the rise time contribution by each element of the link, equation 8.4, where T suffix I is equal to rise time contribution by each element of a link. T system is equal to T Tx square plus T mod square plus D GVD square plus TRS square 1 by 2, equation 8.5, where T Tx indicate transmitter rise time, T mode indicate modal dispersion rise time, T GVD indicate group velocity dispersion rise time, TRX indicate receiver rise time. Let's solve the example. We begin by specifying a data rate of 20 Mbps per and a bit error rate of 10 raised to minus 9, like at most one error can occur for every 10 raised to 9 bits sent. For the receiver, we choose a silicon pin photodiode operating at 8590 nanometer. The receiver input signal is a minus 42 dBm, 42 dB below 1 millivolt. We next select a gallium aluminum arsenide LED that can couple a 50 milliwatt minus 30 dBm average optical power level into a fiber fly lead with a 50 micrometer core diameter. We thus have a 29 dB allowable power loss. Assume a further that a 1 dB loss occur when the fiber fly lead is connected to the cable and another 1 dB connected loss occur at the cable photoreceptor interface, including a 6 dB system margin. Find the total optical power loss. If alpha f is equal to 3.5 dB kilometer, then 6 km transmission path is possible. So let's try to run this particular example with the help of equation 8.2 and 8.3. So system margin is 6 in dB, then alpha is equal to 3.5, attenuation dB per kilometer, L is equal to 6, length of transmission path in kilometer, LC is equal to 1, connector loss in dB, and PT is equal to 2 LC plus alpha into L plus system margin. And finally, displaying with the help of this particular function, the total optical power loss in dB. And result, the total optical power loss in dB is 29. Let's try to check this result with the help of Scilab. So, equation 8.2 and 8.3 are used to solve this particular example. Clear and CLC for clearing the variable browser, CLC for clear the console window, and close any other file is there. Then system margin, alpha, L, LC are given, and we have used the particular equation PT. So let's try to execute this code. So the total optical power loss in dBpt is equal to this 29. So we get this 29 as a result, and the same is printed in this particular answer sheet. Okay, so that is the first example. Now second question is, question 2, we assume that LED together with its drive circuit has a rise time of 50 nanosecond. Taking a typical LED spectral width of 40 nanometer, we have a material dispersion related rise time degradation of 21 nanosecond over a 6 kilometer length. Assuming the receiver has a 25 megahertz bandwidth, the contribution from the receiver is 40 nanosecond. If the fiber we select has a 400 megahertz dot bandwidth distant product and with Q is equal to 0.7, and then modal dispersion induced fiber rise time is 3.9 second, find link rise time. So we have to use the given data into and use equation 8.4 and 8.5 to solve this particular equation. Clear CLC in close, then TTX is given, that is a TTX equal to transmitter rise time, TMAT is equal to material dispersion related rise time, T mode is equal to 3.9 is to 0.9 rise time resulting from modal dispersion, TRS equal to 14 e raised to minus 9 receiver rise time, and then we use the equation T system, that is equal to square root of TTX square plus T material square plus T mode square plus T Rx square, and finally display the result with the help of this function. So let's try to check this example in the Scilab. So we have to use equation 8.4 and 8.5 to solve this particular question 2. Clear to clear variable browser, CLC to clear a console window, close any other file is open, then we have to use the given data TTX, TMAT, Tmode and TRX, and finally use this equation system, that is of square root of TX square plus TMAT square plus Tmode square plus TRX square, and finally displaying the result. Let's try to execute this code. So answer is link rise time in the nanoseconds case is equal to 29.617731. Okay, so the same answer is there in this particular document. So that's it. Conclusion, this experiment is about to know what is digital transmission system. This experiment also demonstrates mathematical equation with example for digital transmission system with the help of Scilab. Note demonstrated example are given in optical fiber communication Gerd Kaiser McGraw-Hill 3rd edition book. Earlier in our video we have used a senior later example that given in the note. In this particular practical we have used Gerd Kaiser book and example numbers 8.1 and 8.3. Thank you.